This is the first lesson of Chapter 6, an introduction to metabolism. In this chapter, we'll be talking about some overarching topics that will help us understand some of the future chapters, such as photosynthesis and cellular respiration. So it's important that we start with some of the basic foundation concepts in this chapter. Metabolism is the sum of all chemical reactions that take place within an organism. And this is an example of an emergent property of life. If you recall from our first chapter, we learned that emergent properties are new properties that emerge because of interactions among different levels of organization. And it's also the idea that as we go from the simpler to the more complex levels of organization, that these new properties arise. So metabolism falls into that category because all of the cellular components and tissues and organ systems and the interactions of those are going to allow for the metabolism in that organism to occur and for them to ultimately survive. Now, in order for an organism to metabolize and for those chemical reactions to continue, there needs to be a source of energy, a way for the organism and the cell to perform work. And there's different states that energy can take. Some of these states can be used directly to perform work, and some are there for storage purposes, but ultimately they can be converted into the form that can perform work. So we can look at energy into two major categories. We can put them as either kinetic energy or potential energy. Some examples of kinetic energy that we'll explore deeper in this class are thermal energy, or heat is a form of kinetic energy, which is energy in motion. So when molecules are heated up or when temperatures rise, the random motion of the atoms and the molecules actually increases. Light is another type of kinetic energy. And as we'll study this in the chapter on photosynthesis, light travels in photons, and those photons can excite electrons, and that is actually what triggers the energy needed for photosynthesis to occur in a plant cell or a cell that has photosynthetic pigments. Potential energy is energy that matter possesses because of its location or structure. And chemical energy is potential energy because of the bonds that are holding those molecules together. And when bonds break, there's energy that's released in that during that chemical reaction. So energy can be classified as either kinetic or potential, but energy can be converted between kinetic and potential and vice versa. How is this possible? Well, we're going to look at that through one example of an archer pulling back on his bowstring, going to release the arrow, and then it will strike the target. So we're going to watch this animation, and there should be a narrator explaining and speaking how this relates to energy conversions. If for some reason you don't hear the audio, you can watch this video through the PowerPoint by downloading the PowerPoint and make sure that your audio is in fact on. But I'm going to give it a try here. Okay, just going to try to mute my microphone first and then I'll play it. Okay, so I hope that explains how we can see a conversion of potential to kinetic energy. Think of other examples in your daily life. In the classroom, we'll be doing an activity with kids' toys to show how energy can be converted in a kid's toy to operate that. All energy is governed by the laws of energy transformation. So we're going to briefly talk about the laws and then how this relates to a biological system. The first law of energy transformation, or you might have heard of it as the law of thermodynamics, states that energy cannot be created nor destroyed. As shown here in the illustration, there's two boxes on, apologies, two boxes of energy on a scale, and it's perfectly balanced where the amount of energy before and after an energy transformation is the same. But you might notice that the box containing the energy after the reaction looks different. The type of energy is not the same as the energy that started. And that's where we observe the second law of thermodynamics. What happened there? Why is that change happening? So with the second law of thermodynamics, we see that there's less usable energy available after each energy transformation. So they basically collapsed the diagonal lines, the grays and the blues, and stacked them up so you can see the amount of unusable energy after, the bottom in gray, and on top of that is the usable energy after. Another way to think about this is by the graphic on the bottom, and for a closed system where energy can't enter or exit the system, it's just contained within that system. As energy is transformed, there's going to be a decrease in the amount of free energy available to do work, or delta G, and an increase in entropy, which is also this term for the unusable energy, or delta S. Let's relate this to a biological system, how the second law of energy, second law of thermodynamics, or second law of energy transformation applies to a simple food chain. A simple food chain has a primary source of energy, typically, which is the sun for a terrestrial food web. There are some exceptions to that. For example, the deep sea, where you have these hydrothermal vents, and there's no influence of the sun directly. Instead, you have chemical energy coming from the chemicals coming out of the hydrothermal vents. But we're going to use this example because it's easier for us to perceive and observe this in nature. So energy from the sun is ultimately fueling this entire food chain. And the first organism that can harness that energy from the sun would be the producers, like the plant shown here, the grass. Now, the grass itself needs to use some of that energy to survive for its own metabolic processes. So ultimately, the grass, through those metabolic processes, is going to give off heat. Heat is energy, but it's low quality energy and it can't be reused. In fact, that would be why entropy would be increasing, because at each stage of the food chain, each organism is giving off heat to the biosphere, to the Earth's systems, and that heat contributes to entropy or disorder, and that is always increasing. That heat cannot be reused as a quality source of energy. The only energy that can be harnessed to do work would be reflected by the yellow arrows. So now let's take a look at the next organism in the trophic level. The second trophic level includes primary consumers like the mouse. So the mouse is getting energy from the grass by consumption, by eating the grass. And the mouse is doing its own metabolic processes, running around, growing, eating, etc. Everything it does just stay alive. And so as a consequence of that, the mouse gives off heat, just like the grass did. And so you see that trend for all the organisms. That's their own metabolism giving off heat. So what's happening though, you might notice, is that the yellow arrow is getting progressively smaller and smaller and smaller. And this is because at each energy transfer, only about 10% of the energy from that previous organism is available for the next organism in the food chain. And so when the mouse transfers energy to the snake, the arrow's even smaller because it's really like 10% of the 10% that came from the grass. And then for the hawk, he's getting 10% of 10% of 10%. So ultimately, the highest level consumers are really having to work harder to get enough energy to sustain themselves. Or probably they're adapted to maybe not eating as often, but getting like a large prey item less frequently. So, and this is also why you see in an ecosystem, like if you were on campus walking around the lake, you might see like one or two birds of prey flying around above the lake, but you might see on the ground level more, you would see more secondary consumers, perhaps a snake, but they're a little more elusive. Maybe you'd see some birds like the ibis, perhaps they're secondary consumers. They're going to be eating things like bugs that are in the grass or in the mud, and then the bugs that they're eating might be foraging on vegetation. So that would reflect like what we would see on campus. You'd see a lot more bugs than you would um, the ibis that eat the bugs. And if there's a bird of prey like a hawk that might eat the ibis, perhaps, then you'd see even fewer of them. So try to apply this to your daily life as you're out and about. Go for a nature walk, or just maybe on a break between classes, walk around the campus lake and see if you can relate what we've just talked about with the second law of thermodynamics to a real biological system. Okay, we're going to leave it at that for the first lesson of this chapter. In our next lesson, we'll look more at other topics about energy and specifically Gibbs free energy, and then get into enzymes.